Okay, guys, here we go. 13.7, change of variables in multiple integrals. So this is the last section we'll do in chapter 13. Then we're going to move on to 14, which is we're going back to vectors again and going to develop some pretty important theorems about kind of vector calculus over vector fields. So before we get there, though, we're basically going to talk in this section about, we did well, you remember, of course. Let's say we were going to integrate something like this back when our lives were just hanging out in the xy plane, right? Of course, we would do a U-substitution here where I would let u equal 1 plus 4x. My du, you know all this, is 4 dx, right? And so we rewrite this integral as the square root of u du, and then we had to change our bounds, right? The whole idea here that we don't talk about very much is we've basically done a transformation where we've defined u, okay, in terms of x, okay? So I know it looks like we kind of go from left to right, but really what we've kind of done is we've gone from right to left. We've taken u and we've transformed it into 1 plus 4x. So that's kind of the idea of what we're going to do today. How does substitution work when we have multiple integrals? Because if you look at this, before we were finding, right, the area under this curve right here, which in this case would look, if I keep saying I'm a lot right now, if x is 0, then I'm up at 4, right? If x is 2, I'm up at 3 times 4, which is like 12. So what we have really is just the area under this right here. And when we do a U-substitution, we're not in the xy plane anymore, you guys. We're not in the xy plane. We're in some plane where u is my independent variable, and then we have, some function, f of u maybe. Let's, some function like g of u or something. So what we have here, remember we had to change the variables. When x is 0, u then is 1. When x is 2, then I find that u is 9, right? So now, if I think about this in terms of area, what we've done then is we've said, okay, this area right here is equivalent to this area right here. So what we're looking at is we're looking at comparing the same areas. Okay, we're taking this kind of transformation in the u g of u plane, and we're making it equal to what we have in the xy plane. So that's going to be the whole idea here when we're doing these change of variables. Okay, you've already seen we've done change of variables. For example, if we had the integral from 0 to 2, 0 to 4 minus x squared e to the x squared plus y squared. So we've actually already done this. We just haven't kind of defined it the way we're going to define it today. So if I switch this into polar coordinates, if you notice, that'd be e to the r squared, rd theta, or rally cry. And what is this? This is a semicircle of radius 2. So r is going to go from 0 to 2. X is just going from 0 to 2. So theta is just going to go from, that'll just be that first part. So this will be 0 to pi over 2. So we've actually done transformations of variables before. We just are going to get a little bit more crazy with them now. So a couple things here to talk about. So when we talk about a change of variables in double integrals, I just want to write down a couple of notes about this. This isn't really, oh, sorry about that. About my phone, that probably messed it up, the video a little bit. My phone went off. All right, so a change of variables and double integrals. This isn't really a theorem or anything. It's just a couple of things about them. So what we're going to do is we're going to look at a transformation that relates some point uv, like in my plane u. Now I need a v though, right? And xy. I know I hate the uv's as well. If you really want to change that to like s and t or something, you're welcome to do that. And the second thing here is how will I define this? I'll say then that x and y can be defined by this transformation of u and v. Okay, so for example, up here I could solve for x and I could get x by doing things to u, or vice versa. Okay, so I have xy is this, where how do I get my x and my y? T is given by this transformation. X equals g of uv, y equals maybe some other function of u and v. Okay, and the idea here, I'm going to sneak this under here, is that I'm excuse me, I'm in some, some blob, I'm going to call it some blob from R, and that uv is going to be mapped by t onto xy, right? So again, the idea here is that whatever I make my substitution to be, and I know this is going to sound a little bit backwards, but everything here, right, is going to be equivalent to something here just by applying these little transformations. Again, I think once I do the examples for you, as usual with all of this stuff, it's pretty easy to see what's going on. Again, we've already done this with polar coordinates. There's a good example that they give in the book. I'm not going to spend time to do it on this because I don't want this lecture to be too long. But if you look on page 1035, that number 1 example just gives you an idea of the image of a transformation. And it's a pretty good little example using polar coordinates, something that we have already dealt with. Okay, so I just want to get into the examples. So before we get there, a couple things here. What we need is this transformation to be 1-to-1. So let's define that really quick, what a transformation is to be 1-to-1. And basically, remember with a function in college algebra, a function is 1-to-1 if it passes the horizontal line test, meaning no two inputs share the same output, right? So we know that for a function, no one input has two outputs, but now we're saying that if I have two inputs that go to the same output, they must be the same input, if that makes sense. So I'm going to say here, I'm going to show you a little bit of notation that's different from your book, but I'm going to call a transformation, let's call this t, and then these little colons, this colon tells me where t is going. So this t is taking things in S and mapping them into R. This is what we say 1-to-1. And we say it's on S because that's what it's mapping from. If T of P equals T of Q only when, so we have two images are the same, only when P is equal to Q, where P and Q are just points in S. And I forgot to tell you, write one thing down. This R right here is the image of S under T. So sometimes you might hear me say things like this is the image of that under that. That just means that when T applies whatever it rules are to S, it's going to map those points from S into R, and R is what we say is the image of S under T. All right, people, just need to, okay. So what our goal is, our goal then is to take a double integral that is defined over some R, and I know this is going to look a little backwards from how we're defining this. But what we want to do is we want to transform it into some integral on S, where we transform, your X and your Y into functions of U and V. And then I have this dA. And then why would we do this? Well, the reason is, just like we did with polar coordinates, is it might make it more simple for us to evaluate. My first example I'm going to give you is not more simple, but eventually it will be. Right, we need one more definition and then a theorem, and then we will be raring to go. Okay, so quick definition. So given, I'm not going to use how your book does this. Given T, X equals G of UV. So here, this is just setting up my transformation. Y is H of UV, where I'm just going to tell you right now, G and H are differentiable. Whoa, I don't know why I capitalized that. Okay, so given that this is true, The definition I want right here is called the Jacobian, and I'm not sure if you, whoops, stop. Okay, sorry. I ignore a lot of features of my surface, and so sometimes they pop up and I don't know how to get rid of them. So the Jacobian is what we're going to define today. So the Jacobian of t, of this transformation, is, here's what it's given by. This is not going to make much sense, and I'm not going to prove this to you, so you're just going to have to believe me. It's going to be the determinant of this matrix, okay? Oh, whoops, that's not what I wanted. I want x. So partial of x with respect to u, partial of y with respect to u for the first column. Then the second column is going to deal with the v's. So remember, when we do a substitution, a u substitution, right? We have to, so this is the determinant. So again, I would just do that cross multiplication and subtract. Let me just write in this little like space right here. Remember, when we take an integral in terms of f dx and we rewrite it in terms of u, remember that this x right here, when I make my substitution, I replace it with du equals g primed of x dx, right? So this is the same idea here, is I want to figure out how to rewrite this dA, right, in terms of u and v. And what does that for us is the Jacobian. I think in the back of your book, maybe they prove this for you if you really can't sleep tonight and want to know why that is true. I think they kind of show it to you in the back of your book. So you're welcome to look at that. But this is what we're going to use to replace this dA. So over here, that's just going to be our Jacobian of uv. And then I'll, of course, have a like du dv or dv du, depending on what way I want to do it. All right, you guys. So I'm ready for my theorem, and then we will get to some examples. Okay, so here's my theorem. So let's set this up well. Let's let t, which again is this x of guv, y equals h of uv, be a transformation. So it's just a mapping. That's all you want to think of. That maps S in the UV plane into R in the XY plane. Into, excuse me, R in the XY plane. Okay. A couple things here. Assume T is 1 to 1, so I'm going to do shorthand. I just do 1-1, okay? On the interior of S, okay, we don't have to, sometimes it's not going to be 1 to 1 around the boundaries of S, and that's okay. On the interior of S, and let G and H have continuous first partial derivatives on that, on S. Because of the Jacobian, right? Because the Jacobian is going to involve the partial derivatives of those guys. Oops, on S. Okay, if, oh my goodness, F is continuous on R, then here's what we can do. We can take that double integral of F on R, right? And it's in the XY plane, right? And we can, basically what we're doing is kind of inverse transformation, but I just don't worry about like which way these transformations are going. What you want to just worry about is actually doing the substitution and figuring out your bounds. Doing your bounds is going to be the hardest thing. Sometimes one of the hardest things is, sorry, let me write this down. This is the absolute value of the Jacobian, okay? So the Jacobian itself is a determinant, which could be negative, but you want to take the absolute value of it. Anyway, sometimes it's hard to figure out what you're going to let u and v be, and sometimes you're just going to be given what u and v are, and those are kind of nice because then you just work with those. So let's do a couple examples, and then we'll call this good. So let's do an example. Clear this sucker out. All right, so, well, actually, the first example I want to do just for fun is I want you to find the Jacobian of r cosine theta, r sine theta, which this should look familiar, right? Because remember, this would be my x, and this would be my y for my polar coordinates. And so my Jacobian in this case, then, what you want to think of is just like your u is your r, and your v is theta, right? So if I were to find the Jacobian of this, then I would have the partial, I want the partial of x with respect to r, so that'd be cosine theta. Partial of y with respect to r is just sine theta. Then I want the partial of x with respect to theta, so that's negative r sine theta. And then the partial of y, right, with respect to theta would be r cosine theta. And so look at what we're going to get here. We're going to get r cosine squared theta minus a negative r sine squared theta. Or if you look at that, notice that's just r. So that r comes from my r dr d theta. So all, that's not a proof of why the Jacobian works, but kind of makes sense why that would be working. Anyway, I thought that was kind of fun to show you. I'm going to clear this out. So if you want to pause, you can. All right. So I want to do a couple of examples. So my first example, I want to evaluate this double integral. We're going from 0 to 4, and then we're going from 1/2 y up to 1/2 y plus 1 of x minus 1/2 y dx dy. So I want to evaluate this by using the following substitution. I want to use the substitution. Okay, I'm going to let x equal u plus v and y equal 2v. Okay, so a lot of times we'll just tell you what the substitution is to use. Sometimes that's just to get you practice with setting these up. Some of the other ones, I'm going to do 2 more examples for you. Like one of them is quite obvious, the substitution we want to use, and then another one not quite so obvious. But this one I'm forcing you to use the substitution. X equals u plus v, y equals 2v. So it's going to be pretty obvious, like when I integrate this, right, I can find the Jacobian right now. That's not hard because I have x in terms of u and v, same with y. I can also just straight plug in u plus v for x and 2v for y and go at this. The issue is when we look at the area that we're integrating over. So if I look at the area that we're integrating over, if you notice, y really quick is going to be bounded by 0 to 4. So I'm going to graph this, and I'm going to try and make that line more of a line. So I'm going to graph this, right? So I know that y is going to be bounded from 0 to 4. Okay, so let's see where x is bounded from. If I plug in y equals 0 into 1/2 y, I get 0, right? Let's use a different color here. If I plug in 4 into 1/2 y, well, that would be, then I'd be at 2, right? So x would be, whoops. So if I plug in 1/2 y, then x is going to be at 2, or 4, excuse me, into 1/2 y, x is going to be at 2. So when y is 4, x is 2. So 1/2 y then, oh man, it is tough to do lines on this. 1/2 y is going to be that guy. And then 1/2 y plus 1 is basically going to be this guy shifted over 1, right? But we can plug in the points if you want to, just to make sure we get that. If I plug in 0, I'm at 1, right? If I plug in 4, I'm at 1/2 of 4 is 2. And then if I put 2 plus 1 is 3. So at y equals 4, I'm over at x equals 3. Remember, I'm plugging in y values and finding x values. So this is my r, okay? And I need to figure out, all right, I need to figure out what this area would look like under these transformations here. Well, one nice way to do this is to just take your points that you have. So I have the points 1, 0. I have 0, 0. I have, what is this, 3, 4. And I have, no, I'm sorry. I'm messing up my y's. Yeah, no. That was right, Sarah. Come on, Sarah. That was right. I have 3, 4, and then I believe I have 2, 4. So one way you can do this transformation is just by actually building like a little table and seeing what happens from my xy under this transformation. What would I get for my uv? Now, the problem with that a little bit is if you notice, I need to plug in x and y and figure out what happens to u and v. So the problem is I need to solve for u and v in terms of y and x. So v then is just going to be 1/2 y, okay? And if I take this 1/2 y and I substitute that in for the v here, then I can solve for u. And so I would get u then is x minus 1/2 y. I hope you see that. So I just need, when you do these substitutions, you're going to need both ways. You're going to need x equals a function of u and v, y equals a function of u and v, and then you're going to need to solve so that you get u equal to a function of x and y and v equal to a function of x and y. Okay, so if I plug in 0, 0, so what would u be when x and y are 0, 0? Well, obviously that's going to be 0. What is v going to be? That's going to be 0. So I know then that that point 0, 0, right, in my S plane right here is just going to go to 0, 0 here. All right, so let's look at 1, 0. So when x is 1 and y is 0, u you see is 1 minus 0, which is just 1. And when y is 0, of course, we just get 0. So for right now, we've actually just mapped those 2 points back to where they were. So I know I get this point right here, okay? Then I'm going to do 3, 4. Now we're going to get something a little bit different, which is more interesting. So I'm going to plug in the 3. 3 minus half of 4 is 3 minus 2, which is 1. And then if I just plug in 4 for y here, I get 2. So that point 3, 4 actually maps to the point 1, 2. And then the final one, which is 2, 4, right? If I take 2 minus half of 4, that's 2 minus 2, which is 0. And then half of 4 is 2. So if you notice, what we end up getting is just this rectangular region, which is great because that's easy to integrate over. Now this is my new region S. So just like when you change your bounds with regular substitution, these are going to be my new bounds for my double integral. So a couple things we need. We need the Jacobian, right? So the Jacobian of uv, remember, is the partial of x with respect to u, which is 1 in this case. And then below it, the partial of y with respect to u, which is 0. Then I need the partial of x with respect to v, which is 1. And then the partial of y with respect to v, which is going to be 2. And if we take that Jacobian, we get 2 minus 0, which is 2. And then I'm going to take the absolute value of that. So it just, the reason we take the absolute value is because then it doesn't really matter what you define u to be or what you define v to be, right? So if we take the absolute value, it doesn't change that. All right, so what does all of this crap right here will become? So what I'm going to get then is I'm going to get this double integral. X is going to be replaced with u plus v minus 1/2 of y, which is 2v. And then we can decide what to integrate first by. It doesn't matter, right? We just need to make sure we satisfy this guy right here. It really doesn't matter because it's a rectangular region. If it wasn't a rectangular region, I would want to integrate, with respect to whatever the variables are first. But we could just do, oh, whoops, I forgot my Jacobian. So I'm going to have 2 times du dv. So remember, this is u, this is v. So u is going from 0 to 1, and then v is going from 0 to 2. And you can simplify this, and oh, I need some better parentheses there. That 2 is times everything. So we could even bring that 2 out. I'm going to go from 0 to 2, 0 to 1. What do I get? U plus v minus v. So my v's cancel, so I just get u du dv, and I'll let you finish all of that. And I believe once you figure it all out, what we get is this nice answer of 2. So I know this can be a little bit complicated. I hope that kind of makes sense. Let's get another example. Let me clear this one out. All right, so another example. All right, so I'm going to need to evaluate this guy here. Y minus x all over y plus x. So that is e being raised to the y minus x over y plus x dA, where R is the region with vertices. Okay, here are my vertices, 1, 0, 0, 1, 0, 2, and 2, 0. Okay, so, I mean, obviously, I can't really integrate this. I mean, I can't really integrate it. I could do maybe a partial fraction decomp on the exponent and then try and like break up my e somehow, but that's just going to be harder, right? So we're going to do a couple things that might make sense. Now, I'm not giving you a substitution on this, but if you notice, I kind of have this fraction built up into two different things in terms of x, y. So it might make sense to say, okay, I'm going to let u equal the numerator, or v equal the numerator, it doesn't really matter. And I'm going to let v equal, okay, the denominator. So that's going to be helpful for us because then, well, right now it's going to be super helpful for us when we switch my r and my s, but it just that kind of makes sense. So here's my r. My r is going to be from 1, 0, right? 0, 1, 1, 0, 0, 1, and then I have 2, 0, and okay, so look at what I'm going to get. I'm going to get something kind of looks like this. So here is my region, right? I have 1, 0, 2, 0, 0, 1, and 0, 2. Okay, again, I'm going to do the same thing. I'm going to create my little table here. Now, I want you to know this works, the table with the vertices works really well when I have lines that are bounding. We're going to see one where I don't have lines, and then it doesn't work quite as well. So you have to be a little bit careful about that. But let's see. Okay, so the point 1, 0, I already have these guys in terms of x and y, so this is going to be pretty easy. What would u become? It would be 0 minus 1, so I would have a negative 1. V would be 0 plus 1, which is 1. So I'm going to go from R to, actually I'm going to need to, because I know what's going to happen here. Okay, so I know I'm going to negative 1, 1. All right, so let's plot that point right there. Okay, then 2, 0. Right, I'm going to take 0 minus 2, so that's a negative 2, and then 2 plus 0 is 2. So I know I'm going to be at a negative 2, 2 there. Then if we plug in the rest of these here, let's look at 0, 1. Well, that's going to be 1 minus 0, which is 1, and 0 plus 1 is 1, 1. So I'm going to be right there. And then finally, 0, 2, right, is going to be 2, 2. So what I get then is I get this region bounded by these vertices right here. Okay, so this region's a little bit different than the one before. It's not going to be quite as straightforward because it's not a rectangle, but that's okay. I mean, if I look, so let's look at what happens here. Remember, if I label my axes here, this is u, this is v, right? So this right here, if I'm going to look at this function right here. Now, this function, look, it goes from the point 1, 1 to 2, 2. And it would, if I come down and over 1, you see I would go through the origin. So this line, this is a line of slope 1 going through the origin. So think of u as your x, v as your y. This line would be y equals x, or in this case, it's going to be v equals u. And then same thing with the line over here. It's the same. It's going to go through the origin, but with a negative slope. So this is going to be v equals negative u. I hope that makes sense. And then, of course, u is just going to go from what, -2 to 2, it looks like, right? So I hope that kind of makes sense, maybe. Yeah. Is that what I wanted? Yeah, because we're going to, actually, we're going to slice them up the other way, right? We're going to slice them up. Oh, yeah, I'm so sorry. We're going to slice them up this way. So actually what we're going to look at is u equals v and u equals -v, because we'll slice them up this way, and then we'll go from 1 to 2. Okay, we'll worry about that here in a moment. But I hope that makes sense, okay? The other tricky part that can be about this one, okay, so I have my region that I've transformed. Now I need my Jacobian. So the rest, this is just algebra, and I know just algebra means that it can be scary and hard, but let me show you what I mean by just algebra. I need to solve these somehow. I need to solve for x equals and y equals so that I can find the derivative easily. Okay, so one way that I could do that is I could just add these two together, right? If I add these two together, I get u plus v equals 2y. So look at that. Then I know y is going to be 1/2 of u plus v. Does that make sense? So I need to find some way to put these two together. And now I need to figure out, right, well, how do I solve then for another one? So if I, now, sorry. Now, what if I wanted, let's get rid of the y's now. So how about we subtract these? So if I subtract these two right here, then I get v minus u equals, the y's would cancel, and I get x minus a negative x is a positive x. So I get 2x. So that means x then is 1/2 of v minus u. Okay, again, why did I need those? Because I need to find the Jacobian. So the Jacobian then of uv here is going to be the partial of x with respect to u, that's a -1/2. Partial of y with respect to u is 1/2. Partial of x with respect to v is a positive 1/2. Partial of u with respect to v is a positive 1/2. And so if you do this, what we end up getting is a -1/2, because you get a -1/4 minus 1/4, which is a -1/2. And then, of course, we're going to take the absolute value of that for the Jacobian. So here we go. We're ready finally to do our substitution. Okay, so I'm going to have e to the top is going to be u, the bottom is going to be v. Okay, and if you notice, I can't really integrate with respect to v first because it would be too difficult because that v is in the denominator. So I want to integrate with respect to u first, right? So again, if I look back at this, u is this direction. What is u going to be bounded by? A -v if I solve for u here, to v, and then where is v going from? 1 to 2, and then I forgot my Jacobian, you guys. Can't even say that's your fault because you're not here. Hopefully you were yelling at the screen. 1/2 du dv. I hope that makes sense. Really quick, I just want to show you when you take the I'm not going to do this whole thing for you because I have one more example I want to show you, but when you take the antiderivative of this, you get 1 to 2. So I have u, right? I'm integrating with respect to u, so I'm just going to rewrite it, and then I'm going to divide by the derivative of u over v with respect to u. So the derivative of u over v with respect to u is 1 over v. And if I divide by that, I just get v. So this one's kind of crazy. -v to v. Oh, I have the 1/2 out here somewhere. dv. So when you plug those in, what ends up happening is you get 1/2, the integral from 1 to 2, so it's squishing a little bit. When I plug in v here, I get e to the 1, so I get v e. Remember, v is a variable. When I plug in the -v, I just get v e to the -1 dv. Then you could even factor v out and put that e minus e to the -1 out front. So you end up getting like some crazy solution with like a bunch of e's like in the numerator and denominator and stuff like that. But I'll let you finish that. I hope that makes sense. I want to do one more and then we'll call it good. So what I want to look at is, well, this pretty specific example. Okay, calm down. This pretty specific example. Sound like my 5-year-old. About where I have like this kind of parabolic rectangle a little bit, and this is the example from your book, but it actually turns out to be pretty sweet, so that's why I want to do it. R of y squared dA. Okay, I want to evaluate this, where R is the region in the first quadrant bounded by, now this is going to be a little crazy, but it'll be all right. Okay, bounded by the following functions. X equals y squared, which remember, that's just a parabola on its side, so don't freak out by that. Okay, x equals y squared. X equals y squared minus 4 is just that parabola on its side shifted to the left 4. X equals 9 minus y squared, that's just the parabola shifted to the right, 9, but pointing now toward the left, opening up toward the left. And x equals 16 minus y squared, which again is just a parabola shifted to the right, opening up the wrong way. So let me show you what this kind of looks like, and this is just going to be kind of a general sketch. So this x equals y squared, right, is just something like this. That x equals y squared minus 4 is just going to be a parabola shifted over 4. And then what you end up getting with this guy is, so negative y squared is just a parabola opening up like that, and then I'm just going to shift it over 9. So wherever 9 is, right, let's say that's 9. And then the same thing with 16 minus that, we're going to shift it over 16. So this right here is what my R is going to look like. It's kind of like this parabolic rectangle kind of. I know that looks super confusing as to what's going to happen here, but it actually is going to work out pretty nice. Now, the Jacobian isn't pretty nice, but it actually works out pretty well. So really quick, notice, let's look at these a little bit. And what I want to do is I want to see if I can find a pattern. If I subtract that y squared, I get x minus y squared equals 0. And same thing here, if I subtract that y squared, I can get the same type of function on the left-hand side. So I get x minus y squared equals 4. And then here, if I add that y squared over, I get x plus y squared equals 9. And if I add that y squared over here, I get x plus y squared equals 16. So what this is telling me is a thoughtful choice for my substitution might be letting u equal x minus y squared. Oh, guys, I'm sorry, that's a negative 4, right? Negative 4. I might let u equal x minus y squared, and then here I'm going to let v equal x plus y squared, right? Because it'll be fairly simple then to see what u and v are bounded by. I mean, if you just look at this, then u is going to be bounded by from negative 4 to 0, right? And then look at what v, the smallest v gets is 9. And the biggest it gets is 16. So the lovely thing about doing one of these kind of parabolic rectangles is we see that my S just becomes this little square up here. And so the bounds for my integration are going to be just constants, which is really nice. Now it's really, really nice that we have just constants, right? Because then I don't have to deal with how to figure out how to integrate over all of these 4 crazy functions. The hard part about this one is going to be the Jacobian. So let me show you how are we going to solve for x and y, right, to find its Jacobian. So again, I'm going to use that trick where I add these two together. So I would get u plus v, then my x squareds cancel, equal to x, okay? So what do we find then? That means x is 1/2 of u plus v, okay? And if we know x is 1/2 of u plus v, what I can put, I can maybe put this into like one of these equations here. I could, and for sake of time, I'm probably not going to go through the algebra on this, but I could put it in here, or I could put this guy in here, and then I would solve for y, right? And either one of those, and I'm going to go ahead and just tell you what that is. So what you end up getting for y is you get y to be the square root of v minus u over 2. And the reason I don't need a plus or a minus is because all my y's are positive, okay? So all my y's are positive, so I'm going to be good to have the square root of v minus u. So again, if I plug that in there, subtract the 1/2 u plus 1/2 v, and simplify, we get something that looks like this. Okay, so now let's talk about, I'm going to get rid of this so I have some room. Let's talk about the Jacobian. And then I got to be done talking. It's difficult to lecture this long in your office with like no one to break up with questions or something. So the Jacobian then of this guy, this is going to be a little crazy, but the partial of x with respect to u is obviously 1/2. I hope you'll just trust me. Actually, I hope you trust the book. I do. I haven't actually done this, but I trust the book. I think what they did was they rationalized the denominator and then took the derivative. So when they, with this guy right here, I believe they broke up the square root and then took the derivative. And of course the derivative of the 1/2 brings it down on the bottom and stuff. But I'll let you verify that for yourselves, that that is the partial with respect to u. And it's negative, obviously, because the derivative of negative u is -1. And then we get 1/2 again for the partial with respect to v. And the derivative of y with the partial with respect to v is just going to be the same thing, but positive, because your v is positive. And so if you do all of that, what you end up getting is you get 1/2 root 2 times v minus u. Okay, so I get half of this plus half of that equals a whole of that crap right there. Okay, so I hope, stick with me. Come on, guys, stick with me. Let me give myself some room here. Some of the, I just need, I don't want to start a new page because I want you to be able to see this. And this is our last example. It's almost over, yay! Okay. So, all right, so what am I going to get? So remember, what were we even doing, right? We were doing y squared dA. So here's the cool thing. I know that my, it doesn't really matter what we integrate with respect to first. We'll just do u first. So, or excuse, yeah, u first. So remember, v goes from 9 to 16. U went from -4 to 0. Here's my y. The nice thing is if I square that, I just get v minus u over 2, okay, times my Jacobian, which is 1/2 root v minus u, right? And then I'm doing du first and then dv. And this actually works out pretty nicely. I know it looks kind of gross, but I don't know, it's still going to be easier than trying to figure out those bounds of that original double integral that we asked for. So these 2's I'm going to bring out as a 1/4. Actually, I'm also, oh, I forgot my 2 inside, right? So I forgot that 2 inside. I'm going to make that a root 2 out here. I'm just going to factor that out, which, hey, I can do that because it's multiplication. I can break up that square root. So I'm actually bringing the 4 and the root 2 out here. And then if you notice, this guy's to the first power, that guy's to the half power. So this is v minus u to the 1/2 power du dv. And I'm raring to go. So, oh, I forgot my integral. Oh, you guys saw that. I didn't see it. Sorry. So I have 1/4 root 2. I'm just going to take you one more step. 9 to 16. Okay, antiderivative of this, right, is going to be 2/3 v minus u to the 3/2, and then the derivative of the inside is -1, so divide by it, so I get a -2/3 from -4 to 0 dv. You will plug the 0 in for u, you will plug the -4 in for u, and then integrate one more time. Okay, and this one is in your book. I cheated and grabbed this example from your book because I liked this example. It is example 5 on page 1039, 1039 and 1040, and the answer is about 18.79 when you do it. Guys, I'm tired. That was a lot of talking. I bet you're tired too. I hope you guys are hanging out like in the classroom together or something. All right, so let me give you, oh, come on, some homework. By the way, we are not going to do, you can do this in triple integrals also. Fun, right? To take not a solid, but a volume of integration and change it. We're not going to do the 3 variables because we just don't have time as usual in this class. But 13.7, this will be due next Friday, which I believe is the 20th. Is that right? I believe so. And here are the problems I want you to do. 27, 28, 29, 30, 31, 32, 35, and 36. Okay? So due Friday. If you have questions, shoot me an email. I'm in meetings most of the day, but we do have breaks, so I'm happy to answer any questions you have. I will answer questions on Wednesday when I get back, but we have to move on to chapter 14 on Wednesday, so I won't spend a whole lot of time actually like lecturing on this again, but I'm happy to answer any questions on your homework. All right, you guys, I'll miss you, and I'll see you Wednesday.